We are now in chapter 7. And we're going to be talking about work and energy. And what you're going to find out here that I want to look at a couple of things that I would say are physical versus very abstract. So if I was to sort of look at an overview of this chapter, the first thing that I would say here is that we're going to be focusing a good amount on work and something called the work energy theorem. Now, I think this is a really important piece here, because when we talk about work, I would say that work is a physical concept. That means you have the ability to comprehend what do I mean when I say work. Unfortunately, there's this word energy. Energy is this very abstract concept. And the energy that we use in everyday language is not the physics energy. And if you can tell me right now that you find momentum to be this very physical thing, then I'm going to say, then you're going to say that energy is a really physical thing. But I would say that the majority of the people say that momentum and energy are quite abstract. And they really don't exist in the physical world. They exist in momentum and energy worlds. The other thing that we want to talk about here is that we need to, now that we got a sense of what the work energy theorem is, we then define energy using the work energy theorem. And it is the only way you can define work. There is no other there is no other definition of energy than the work energy theorem. And what you find here is that there's this thing called kinetic energy. There's a very broad category called potential energy, which will take quite a bit. And the other type of energy that we'll deal with is thermal energy. And what I would say here is that kinetic energy is about microscopic motions, macroscopic motions. Thermal energy is about microscopic motions. So they're very similar in a lot of ways. Potential, man, that's the big one. It's the most abstract one, and it plays a huge role in physics here. But we'll get to that more a little bit. And then the third thing that we want to do is that we want to go in and we want to look at this concept called conservation of mechanical energy. And when we say the word mechanical energy, it refers only to kinetic and potential energies. If we include thermal, then we could invoke what's called the conservation of total energy, or we could use the work energy theorem. So there's something that we have to sort of like account for in order to sort of like get a sense of how we what we apply and when we apply. So that's the idea. So the first thing I want to do here is that I want to talk about work. And remember what I said about work. This is the physical thing that people understand, not energy. And there's lots of ways that we could talk about work. And I could say that for me, when I was young, my parents owned what was called a paleteria, which was a fruit bar business. And, you know, a couple days a week, they would deliver these endless number of fruit boxes, boxes full of fruit that had to be moved. So I would say that for Carlos, work was moving the endless number of fruit boxes. Oh man. And like I said, I used to despise those boxes. And so the idea here is that when a delivery was made, you had to carry the boxes. Some of the boxes would then go to a table, let's say. So then I would have a box, right? Here would be my box. And let's say this box was full of fruit. We could say strawberries or whatever. And then I would labor. I would definitely labor in moving these endless box. And of course, I was not happy about it. And because I was not happy about it, I would definitely whine in moving these boxes. So the goal here was to move this box over to some location, either in refrigerators or in tables. So what would actually happen in this case here? What would happen here is that in order to move the box, I would have to apply a force. And as I move this box, I would have to do it over some displacement. Now note, I did not say distance. I said displacement. So we could see here is that moving a box requires two things. The first thing is that you have to apply a force over some displacement. So a very naive definition of work is that work would then be equal to force, a combination of force, displacement, combination. So it has to involve both of those things. So then, now let's make a little bit better of a definition. So we could say that the work done by a constant force is then going to be something like this. It turns out that work is equal to force and displacement. Now, it's really, really, really hard to actually say how these are, but there is a multiplication here. And this multiplication is called a vector product. Now, what's special about a vector product is that we know that force is a vector, displacement is a vector. So if you multiply two vectors together, you're going to see here that I'm going to get a number which we call a scalar. So it's not an ordinary multiplication here. Now, it turns out that
Recording in progress.
we can actually do this a little bit more technically, but I think I'm going to just stop it right there. There's other ways that I can write this, and I think I might just save it for Physics 4a because it's more complicated. Most forces are not constant. Most forces depend on distance. For example, the frictional force depends on distance. Therefore, the work depends on distance. And so the force has to be written as a function of displacement. So it's more complicated, but let's just leave it there for right now. And when I look at the units of work, a unit of work is a unit of force times a unit of displacement. And typically we write a displacement as delta x. And this is then going to be a Newton times a meter. And this by definition is a joule, which we typically write that with the J. And we had that with the lab. So what I want to do here is that I want to go in and I want to start to look at this guy in the sense that we start to interpret this. But before I could interpret this thing, we have to look at the work energy theorem, because I can't really write about work without the work energy theorem. So here I go. So now here is what's called the work energy theorem. Oh, come on. So the work energy theorem says that when an external force does work on a system, something about the system changes. It's energy. So it's the energy that changes. So what we then say here is the work done by an external force on the system is equal to the force times the displacement. This is equal to delta E, which is E2 minus E1, where E is called energy. And so this is a systemic parameter that tells us something about the system. So that's a pretty vague statement, but this is the definition of energy. Okay. This is the definition of energy. So my whole goal here is that now I want to start the interpretation process. And there's a lot to unfold here. So when I say the interpretation process, I'm going to talk about work and I'm going to talk about energy here. So let's first talk about work, and then I go right into the work energy theorem. Okay. So the first thing I want to do is I'm going to say this, that work depends on both displacement and external force. Okay. So what I want to do here is that I want to focus on both of these here. So now let's talk about the first thing that I'll talk about. You know what? I should have labeled this because there's going to be a long list. So let me move this over a little bit here. And I'm going to call this one. Okay. So this is the first thing I'm going to do. So let's talk about the displacement dependence. Now note, you know everything about what I'm going to say. It's not a surprise what I'm going to tell you here. But here's what I want you to think about. I'm going to try to move a block. So I imagine that I have a block. And this is the block that I'm going to move right here. Now, what I imagine here is that you're going to be this little person that's going to push on this block, and you're going to move this block. Now, when I look at this thing, what I'm focusing on is that I'm focusing on the block. So I'm saying that my system here is going to be the block. And as a consequence, you're seeing that as this little person pushes, they are applying an external force to this block. And then what are they going to do? They're going to move this block. So let's say here that they move this block this far. So you know what? This system here, I'm going to move away from over here, and I'm going to move it right there. So I'm going to say that my system here is that. So now that I've displaced my block, I'm seeing here that this block has now moved some displacement D in this direction right here. Now, what this is going to refer to, this is going to be my reference. So again, I'm going to move this over. So I need something as a reference. Okay. So this thing is going to be my reference. So everything is measured from this reference right here. Okay. Everything is measured from that. So in other words, if I look at how much work was done, so if I say how much work was done, then I would say that this is what I mean by W. And you can see that I applied this amount of force and I did that amount of displacement. That's how much there. Now, if I want to look at the displacement, what do? I don't change. Let me set this up so that it's nice and clean so that I'm at one of the squares here. So now, what am I going to do? I'm going to do the exact same thing. I'm going to take this block, but now what I'm going to do here is that I'm going to move it this far. So I'm going to move it a farther distance. In other words, my distance now is much. In this case, it should be about twice the distance. But the force that I'm applying is exactly the same. So now, when I look at how the displacement is coming into play, we're seeing here that I'm applying the exact same force, but now my displacement is larger, and as a consequence, I did more work. So if I have to move the same object farther, of course, it's going to take more work. We knew that already. And we could say the exact same thing as if I look at its force dependence. If I talk about force dependence, then if I look at this here, you could imagine that if I again take my exact same scenario here, right? Here's my reference again. I need my reference. So if I copy this and I put this right here, and I'm going to say, here's my reference. Right? Again, here's my reference. Now, if I clean this up just a little bit, now you could imagine here, what happens if I have to move a block that's twice as big, and I moved it the same distance. So if I moved it the same distance, in order to make this move the same distance, this clearly takes more work because now you're having to apply a much larger force in this situation. So when I go look at my work, my original work was this big, and that's because I was multiplying my force like this and my displacement like that. But now, if my force is this big, while my displacement is the exact same, clearly that took more work. That's what I mean by the dependence. So what this is really showing me here is something like this. There is a way to do the same amount of work two different ways. In other words, I could do the same amount of work by either applying a small force or a large force over a big distance versus a small distance. There's two ways that you can do this here. So what I want to do here is that I want to show you just two simple examples and not get too caught up in the details. So let's look at two examples of something like this that are everyday examples. One, let's say that you need to change a flat tire and use a car jack to lift the car. So what happens here? Clearly, you cannot lift the car by yourself. And what you use here is that you use a car jack. So you could imagine that you have a car. Let's say that this is the car. Your car tire is flat. And you're going to change the front tire of the car. So maybe this is your orange Jeep. Okay, so you have your orange Jeep here, and what you got to do here is that the first thing that you got to do here is that you have to lift up the car. So what do? You take a car jack, which somehow connects to the car. And what you're going to use here is that here's the car jack. And you're going to use this car jack to lift the car up. So what you're going to find here is that the way a car jack operates, at least a hydraulic, it actually operates very like a teeter-totter or a seesaw. They act very, very, very similar. And so what you'll find here is that you're going to have a fulcrum right here. And then what you do here, so let's say that this is sort of like your car jack. It's really a hydraulic car jack. What you're going to do here is that you take what's called a tire iron in the old days, and it was a long metal rod. And what you're doing here is that you're going to apply a force to the tire iron. And I should have written that here. So this is the tire iron. And what you do to the tire iron is you actually push it down so that it does something like this here. So what happens here? If you compare the two distances, here's what you're seeing here. As you push down, look at this distance. That distance compared to this distance, that's a little tiny distance. This is a bigger distance right there. So here's what happens here now. The work done does not disappear. But reappears as transferred work. So your work does not disappear. So then the work of the person is then going to be, the way a jack is set up is that you apply a small force and you do this over a large distance. So what happens now is that all of this gets transferred to the car. And in this situation, what you're doing here is that even though you're moving at a smaller distance, you're actually applying a larger force to lift up the car. So then that means here is that you're going to apply a big force, but the cost is that you only lift it up a tiny bit. So when you're using a car jack, what you do here is that you're moving the tire iron numerous times in order to lift up the car sufficient here. So what this is really telling us right here is it's telling us this, that the car only gets lifted a tiny amount per stroke of the tire iron. On the other hand, what typically happens here is that one has to move the tire iron, the iron, numerous times to lift the car. In other words, what you're seeing here is that there's two ways to do the same amount of work. The work doesn't disappear. It just reappears on the other side here. And by the way, that's what we call a hydraulic jack. The other thing here that's worth looking at it is, let's say that you're going to move a refrigerator using a U-Haul truck. Now, there really is two ways to lift a refrigerator onto a truck. So what's sort of like the standard way? You could imagine that I have a U-Haul truck. Let's say this is the U-Haul truck right here. So when I'm looking at my truck, you could imagine, and then this is sort of like the bed of the truck right here. Now, the way most people lift a U-Haul, they use a U-Haul truck, is that, what do they do here? You have a ramp. What comes with the truck here is that you get this thing called a ramp. And that's pretty goddamn important.
Oh, small.
Right? So now you could imagine if you're going to move a refrigerator, let's say this is your refrigerator right here, and your whole goal is to move the refrigerator onto the U-Haul truck, and there's a reason why you use a ramp. So you could imagine here, right? The reason why you do that here is that the first thing that you should note here is that it starts right here. So it starts in the same place, and then here it ends right here. So the distance from the ground to the U-Haul truck is going to be the same no matter what. So there's another way that you can do it, right? If you were an idiot, you thought that you could save money by not getting the ramp on a U-Haul truck, even though they come with that automatically. But your dumbass does what? It says, well, I'm going to save money this time, and I'm going to lift this truck up. And the whole goal is to get the truck onto the U-Haul. So when you're looking at this thing here, note that they start, right? It starts at the same place and it ends at the same place. So believe it or not, Both of these require the same amount of work. But what's the difference? This one requires a small force to do it. This one requires a big force. The cost of doing the smaller force means that you have to move this a larger distance. Here, you just have to move it a smaller distance. In each of these situations, we can say here is that because they both start and end at the same locations, they require the same amount of work. In other words, when I go and I look at the work here, one way requires a small force, the other way requires a big force. But the cost of the small force is a large distance. The cost of a big force is that you have a small height that you have to change it here. Both ways do the exact same work. We can mathematically calculate these guys, and I can show you how that works out here. Okay, so we've done two examples here.